Good morning, class. Today I'm going to review the results of the mock test I gave you yesterday. Today is Thursday, May 28th, Coronachem day 38 for period 4. The first question on the mock test was number 1419. The question asks, consider the combustion of hydrogen gas. It shows you a balanced equation. If hydrogen is burning at the rate of 0.85 mole per second, what is the rate of consumption of oxygen? What is the rate of formation of water vapor? So the stoichiometry of the burning of hydrogen obviously requires oxygen and produces water vapor. And when you balance it, it comes out to 1, 2, 2, 1, 2. It goes 2, 1, 2 stoichiometry. 2 moles of hydrogen combines with 1 mole of oxygen to give 2 moles of water. So, given that, I had it right here. Silly me. Okay. Given the 2, 1, 2 stoichiometry, and you're burning 0.85 mole per second of hydrogen, the O2 consumption is going to be 1 mole of O2 burned for every 2 moles of hydrogen, so 1 to 2. So you get 0.425, and the O2 consumption, no, the H2O appearance is 2 to 2, so it's or 1 to 1, same thing. You get the same amount of water appearing, 0.85 mole per second. In question 1432A, it asks, consider the reaction of peroxydisulfate ion with iodide ion. The stoichiometry is 1 mole peroxydisulfate and 3 moles of iodide produces 2 moles of sulfate and 1 mole of the thiodide ion. Gives you a bunch of data. I only asked you to do A, determine the rate law. This one was a little bit tricky because it had 150% rate increases, but it's actually straightforward. It's first order in both. I'll show you a close-up of my notes where the rationale is given because there wasn't enough room to write it all out on the board. But the rate law is K, the rate constant, times the peroxydisulfate ion times the iodide ion concentration, and they ask you to find the units for the value of K. So the rate over the concentration of the 2 reagents is going to isolate K. So that has units of, the rate has units of molarity per second. The concentrations are in molarity. If you do the arithmetic, you get rate units of molarity to the -1, seconds to the -1 for the value of K. The next question was 37. Asks, as described in exercise 1435, the decomposition of sulfuryl chloride is a first order process. The rate constant for the decomposition at 660 Kelvin is 4.5 times 10 to the -2 seconds to the -1. A, if we begin with an initial sulfuryl chloride pressure of 375 torr, what is the pressure of this substance after 65 seconds? It's a first order process. So we can use A is equal to A naught e to the KT to solve for that one, keeping in mind that it's a decay, so you're going to have a negative value of K. And let me show you what that looks like. So 1437. Part A, we're going to use A is equal to A naught e to the negative KT. Why did I put negative K? Because it's a decay. The thing is disappearing. And K, in this case, equals 4.5 times 10 to the -2 to the seconds to the -1. A naught is 375 torr. T is going to be 65 seconds. And A at
at some time t is what we're looking for. So we set it up. A is equal to 375 e to the negative 4.5 times 10 to the minus 2 times the 65 seconds that elapse. So what you get is 375 e to the power of negative 2.925, which gives you 375 times 0.053 664 691. That's what I got in my calculator readout, and that works out to 20.1245. We're only going to report the 2 sig figs, so it's 20 torr. After 65 seconds, the pressure is 20 torr. And the next part of the question asks, when will the pressure equal 37.5 torr?
At what time will the pressure of sulfuryl chloride decline to 1/10 its initial value? So we're going to do part B now.
1/10 of the initial value of 375, we put it at 37.5. So again, using A is equal to A naught e to the KT. A over A naught is going to also equal e to the KT. Keep in mind that 1/10 of the original pressure means this will be 1 over 10, or 0.1 will equal e to the negative 4.5 times 10 to the minus 2 seconds to the minus 1, and the time is what you're looking for. If you take the ln of both sides, what you get is negative 2.30258 equals negative 4.50 times 10 to the minus 2. When you have something raised, when you have e raised to the power of something, if you take the natural log of it, the e disappears and all you're left with is the exponent. So you're going to solve for t now by transposing that 4.5. So t equals negative 2.30 over, I'm not going to write all the decimal places, you can do that yourselves when you do it in your calculator. What you get as the time interval is 51.168 seconds. You're only allowed to report 2 sig figs, so you're going to say 51 seconds till that 1/10 pressure is achieved. The last part,
The last question I wanted you to do is 57. On 57 it asks, the activation energy of a certain reaction is 65.7 kilojoules per mole. How many times faster will the reaction occur
at 50 degrees Celsius than at 0 degrees Celsius? Oh, that's on the
sheets here. Okay. When you have 2 data points, you can use the equation that appears in the textbook on the page, let me see if I can find the page for you. Part of the Arrhenius law, and it appears on page 598, top of the page. It shows you the derivation for the equation as well. So bottom of page 597 and top of page 598. So 57. The rate of a reaction may be represented by the magnitude of its rate constant.
The difference in rate between two reactions may be quantified by comparing the rate constants at two different temperatures. So what we did is we had ln of K1 over K2, two rate constants at two different temperatures, and we converted the activation energy into joules per mole so that the units would work out. And we used the gas constant 8.314 joules per Kelvin mole. Reciprocal temperatures have to be used, 273.15 represents 0, and 50 degrees Celsius is represented by 323.15. So ln of K1 over K2 is going to give you 7,902. I'm truncating some of the decimals for brevity's sake, but I used all the numbers when I entered it in my calculator. Just this board is so tiny that it's going to get messy if I write all the decimal places. You get the picture, and you'll recognize the numbers if you do the calculation yourself. Now take the inverse log of both sides, and you get the ln disappears here, and you get this turning into 87.909. So the ratio of K1 to K2 will be 87.9. So the reaction will go 88 times faster. At 50 degrees Celsius than at 0 degrees Celsius. That's the mock test, so you can expect something similar to that tomorrow. I'll post the questions. I still haven't chosen them, but they will be similar to what I gave you just now. And also, tomorrow I'd like to start teaching the chapter on equilibria, which is chapter 15. I actually want to go through 2 more chapters. You see how rushed this whole curriculum is to actually do it justice. If I could just run along through it and none of you would get it, and I wouldn't have taught the course. So I'm trying to teach the course at the pace that suits you and I sense that you need, but you realize that we are pressed for time. So there's still chapter 15 I'd like to get through, and there's a couple other chapters I could, in all honesty, attempt, but it wouldn't do much justice to it. We'll try to get to the organic chemistry chapter before the end of the year, which is, I guess, somewhere around June 23rd. Okay, so study your mock test questions, your real test. By the way, your real tests now, okay, this is the last sort of 1 unit test. I'm going to start giving you tests that comprise 2 units. And they're going to count for 10%. I'm hoping to do 3 of those. I'm giving myself a lot of work, but by doing 3 of those, 10% each, it adds up to a total of 30%. So it's going to be one last or a grand review, and then we can end the year that way, and hopefully you'll have learned some chemistry in the process. So I'll see you tomorrow.